very glad to be here. And today I'm going to talk about a point of view on surface approximation and computation of curvatures through varifolds. Okay, so first of all, why varifolds? Okay, for several reasons. First of all, because they're flexible. Okay, you will be able to handle lots of objects with a varifold structure. Okay, you can think of discrete objects, point cloud, triangulations, I don't know, your favorite one. And of course also continuous, regular or less regular objects. Varifolds, essentially, they encode all the one information. Okay, so they define a way to integrate continuous function on the tangent bundle. So they will encode your object and its tangential information, but tangential in an unoriented sense. Okay, so only the direction, not the orientation. Well, as they encode the other one, then they will provide a weak notion of curvatures. Okay, so that's what I'm going to focus on today. And you have natural distances to compare varifolds, okay, that come from, let's say, weak star distances between measures, so that they are adapted to compare geometric objects. Okay. But before that, I like to start with a simple example. Okay, just take a curve gamma in R2 that is closed, smooth, injective, okay? And you can define a unit tangent, and you can define the angle of the direction made by the tangent with the axis, axis, okay? So on this curve, if you parameterize it with a nice arc length parameterization, then your curvature vector is just the second derivative of your parameterization. Okay. Now let's do some simple by-part integration on this curve. Okay. So take C1 smooth function and compute this integral. The boundary term is 0, and there here you see that the curvature appears. Okay? And now if you compute this quantity in another way, then you'll see the projection of the gradient of phi onto the tangential direction. Okay, this thing is just the projection onto the tangent of the gradient of phi. So you have some equality between an integral involving the curvature here and here a derivative of phi. Okay, so you can think of phi as a test function, and here you have a weak notion of curvature. Okay, so you can in this very let's say simple setting see your curvature as some distribution, actually, relying on what? On the fact that you know how integrate onto gamma those kind of function, okay, involving the direction of the tangent and continuous function in x and theta, since this was C1. Okay, so that's what I was saying, actually. Okay, so if you want to compute this thing, you only know, actually even less, but this will be enough, how to compute those integrals. Okay? So those integrals are actually what is called in this simplified setting a varifold. Okay? So varifold is not a very, very technical object. It becomes technical when you want to generalize it to any dimension and codimension, because it's less easy to encode the direction. Okay, you need more than just one angle. Okay, but essentially a varifold in this case will be a continuous linear form on this space, okay? And here, a natural varifold associated to our curve is how I integrate those continuous function and pi periodic with respect to the direction. Okay. So, if you know this structure, V gamma, then you can recover the curvature, because remember that you had this formula here, okay? So that I can rewrite here in terms of V gamma, okay? So if you know the varifold associated to gamma, then you can compute the curvature. And conversely, as soon as you have a continuous linear form on those continuous function, then you will be able to define a weak notion of curvature, okay? So that was a simple example of a curve in R2. And now I'm going to kind of explain how you generalize it to a surface or a higher dimension. Okay, so what is a varifold more generally? It will be a measure that couples both weighted information and tangential direction, but non-oriented one, okay? So if you had an oriented object, you will lose the orientation when you look only at the varifold structure, okay? So varifold is a structure that you can put on an object, okay? It was introduced by Almgren in the 60s and then widely studied by Allard in the context of minimal surfaces. Okay, so generally speaking, okay, technically a d-varifold is a Radon measure on the product of the space Rn times, and this is the Grassmanian, okay? So by the Grassmanian, I mean all the d-vector subspace of Rn, and, okay, I will put that I would embed this space in the matrices, okay, and to one plane, I associate the orthogonal projector onto the plane. Okay, it's a way of seeing Grassmanians that allow you to recover easily a notion of distance between two planes. Okay, not the only way, of course. Maybe not the more natural way to put a distance on the Grassmanian, but for what we're going to do, it's enough. Okay. So the Grassmanian will encode the tangent direction. Okay, now the other term in the definition of varifolds was Radon measure, okay? If you don't like that much measure, you can think of linear form on continuous function, okay? A varifold will be a positive linear form on compactly continuous function on this product, okay? And when you are dealing with such object, then you have structure. You have weak star convergence, okay? That is exactly the pointwise convergence with respect to your test function. And you can locally metrize this weak star convergence with what is called the flat distance. For people that are familiar with optimal transports, if I remove this assumption, then you recognize a way of defining Wasserstein distance, 1, 1, okay? The idea is that here we want to compare not only probability measure, but measure with different masses, okay? So that's why there is that additional assumption in the definition of my distance. Okay, so about this distance, maybe a little bit more. I told you that it was adapted to compare geometric object, okay, to my approximation context. The idea is that if I have a Dirac mass, you can think in R, and another Dirac mass with a slightly higher weight, okay? I want to say that they are close, okay? They don't have the same mass, but almost, okay? And that will be true in, with the flat distance we defined, but if you remove the assumption that the infinity norm of my test function must be bounded, okay? So taking Wasserstein one distance, then that would not be true, okay? You could make easily tend your distance to plus infinity, even though you have epsilon as small as you like, okay? If now I think of the other assumption, I ask that my test function is one Lipschitz. Well, if you remove this assumption, you can take two Dirac masks that are as close as you like, but the distance between them will still be equal to 2, okay? So it's, okay, heuristically, the reason why you have those two natural assumptions, and they will be enough to have, to compare then our objects, okay? And of course, you can also localize your distance by asking that the support of your test function is in some open set, okay? So this is the distance we're going to consider between varifolds. So now, okay, I had a first example of one varifold at the very beginning, okay? Now take also one example, and now I'm going to take the point of view of measure, okay? You can either define linear form on continuous function, on your test function, or take a measure on Rn times the Grassmanian, okay? If you take only one line in the plane or in Rn, then you can take here just the integration measure on your line, okay, or a segment, and on the Grassmanian part, you say, okay, I have an object that is, as always, the same tangent, okay? So the measure you put on the Grassmanian is the same at any point of your segment or your line, and it's just a Dirac mass in your tangent in the direction of the line, okay? That's what means this tensor product of measure, okay? Now, if I take a union of segments, but I can just sum up measure of this type, okay? Here, the notation H1 refers to Hausdorff measure, but you can really think of Lebesgue measure, one-dimensional Lebesgue measure here. Yeah?
At the beginning of your talk, you speak about continuity. And what is the continuity on the corner of your segment?
I speak of continuity.
How do you handle a corner on the contour of the image?
Okay, so you mean here, when you define your tensor product, here, that's right, your tangent direction is not defined as a Dirac mass, but either you can take an average, a sum of two Dirac mass and divide by 2, or anyway, those points have null measure with respect of the integration on your object. So you won't see that. You won't see the problem on that for that respect. Okay, I don't know if it was clear. Okay, and you can do the same with the triangulation. Okay, you say on each face I have a direction, and on each face I take the two Lebesgue measure to integrate. Okay, so on those examples, what's important is that varifold structure really reflects the way you integrate function and your direction. Okay. You can do the same with a set of points. Okay, but to define a varifold, you will need points in your space, masses, okay, and directions, and then you can take a weighted sum of Dirac mass in space and Dirac mass in direction. Okay, so that's also a varifold structure. Okay, now if I come back to more continuous object, regular object, and I take a submanifold, so maybe I can take this. Remember for gamma, the way of defining my varifold was by saying when I test against a function that is continuous with respect to this product, okay, more or less, okay, theta was reflecting the direction, then I define the varifold by this linear form. Then actually we are going to do the same, okay. If M is a submanifold, then the action of the varifold on psi will be I integrate over my surface, psi in the position, and here it's not only an angle that encodes the direction, but a subspace, a d-subspace, okay? And here it's just the measure of integration on your surface. Okay, so think that the varifolds is really a way of putting a nice measure on the tangent bundle. Okay, so space times tangent space. Okay, so it's possible to define varifold structure associated to any submanifold, and also, if you like, rectifiable sets with corner, with edges. The idea being that even though you don't have a tangent plane that is defined when you have a corner, okay, this set where the tangent space is not defined will be of null measure, and it's still possible to work with such sets. Okay, so last thing I need about varifold is to say if I know a varifold, I can define a measure only on the space, okay, that gives me only the action on function defined in space, okay. I can just forget about the tangent direction. Maybe not smart, okay, but then it's just integrating over your surface if you have a continuous object, okay. Well, you can define this in a general way. I'm defining all those things in a general way because then I will work with a general varifold. Okay, so that's why I need this framework. And so maybe to summarize, a d-varifold, so either a Radon measure on Rn times the Grassmanian, or a continuous linear form on a continuous function on Rn times the Grassmanian, you can always see such an object as a measure just in Rn, in the space, okay? And at each point in the support of your measure, or almost each point, okay, you put a measure on the Grassmanian indicating a probability of direction, okay? That's what is a varifold. It's equivalent, actually. It's a disintegration property. Okay, so those are kind of objects you could think of when you think of varifold. You can put a varifold structure on point cloud. We did it. Here, think of a surface, and then we did it also. And here, well, you could say rather than concentrating my information on point, I just diffuse it in cells. Okay, so, but there are lots more of objects you could provide with a varifold structure. Essentially, as soon as you know how to integrate continuous function and you have a tangential information, you are close, or you have a varifold structure. So you remember at the beginning, I show you a weak formulation of curvature for a smooth curve in the plane. So that's something that you can generalize to varifolds because it was only relying on the varifold structure associated to your curve. So this has been done by Allard in the 17th, and the idea is that your formula is more complicated, but it's the same idea. Here you have a differential operator over the 1, okay, so it's a projective divergence. Here you take a test function, you integrate this other 1 differential operator, and on the right hand side you have the mean curvature that appears, okay? So this is close to the more classical divergence theorem in an open set of Rn, but if you were in Rn, here you would have Rn, the classical divergence, and here you would have 0, okay? But here you are in some surface that is not a plane object, and you have the mean curvature that appears and not 0 in the right-hand side, okay? Well, the idea is that, as for gamma before, this formula, the left-hand side, only relies on the varifold structure. You can rewrite it with a technical formula, but it doesn't matter that much. The idea is that only relies on a varifold structure on M, okay? So, and the right-hand side, the only unknown you have here is the mean curvature vector H, okay? Here it was the integration over your surface. Here, or modularly, you must measure. So you have a general formula in varifolds that allow you to define, okay, by this distributional equality on test function x, a notion of generalized curvature. Okay? So the idea is that now, here, V, you can plug a varifold associated with a smooth object, but you can plug a varifold associated with a point cloud, with a triangulation, with any object you like, okay? And it gives you something. Well, next question is, maybe what it gives you is not really that much correlated to curvature when your object is not smooth enough, okay? That's what we are going to see. So, if you want to really define the curvature, then you take your left-hand side, you see it as a continuous linear form on test function, and through this theorem you have a measure. Okay? Well, this is only true if this is continuous for test function in C0, and here I mean C1. So, okay, for instance, for the moment, I only have a distribution of order 1. Okay, generally speaking. If I have a surface, of course, it's much better. And as soon as this is a measure, distribution of order 0, whatever this assumption could mean, it's not very concrete, you can define a generalized mean curvature, okay, essentially by taking the density of this measure with respect to the integration over your object. Okay. Well, and if not, okay? Because actually your assumption saying that, well, this is continuous not only with respect to the C1 topology, but the C0 topology here is not an assumption you can get rid of really easily. If you think of a point cloud, just take one Dirac mass, okay? And try to apply this linear form here. Then here, well, what you will have is a derivative of your Dirac mass that will appear. And a derivative of a Dirac mass is never a Radon measure, okay? So your assumption to define generalized mean curvature will fail, for instance, for point cloud. And for discrete objects, it won't fail, but it might not be that consistent. So for that purpose, we define an approximate curvature based on this notion of curvature. And the idea is that you take your object, okay, that is not regular enough, and you regularize it. So now, not only you have something that is a distribution of order 0, but you have even a nice smooth function, okay? So, and this, if you rewrite this expression here to your convolution kernel, it's quite explicit, okay? Here it's just the projection onto the plane S of the gradient of your profile that you know, okay? And then it's just the integration against your varifold that you know. So to just explain how explicit it is, if I take a varifold associated with a point cloud, then actually you can rewrite this formula just this way, okay? So here a projection operator in Rn onto a space, and just a sum of product, you evaluate the derivative of your profile. It's something quite explicit, okay? Even though it's not clear maybe on that expression. And now this smooth function is well defined for any varifold, okay? And if you want to recover not only delta V, okay, but the integral of the mean curvature, but the mean curvature, well, then you just redivide by the mass, okay? If you want the density, H, then you take this function and you redivide by the area measure, okay, and you have just this density here that appears. You are not obliged to take the same regularization kernel here, and even more, and moreover, it might be more efficient not to take the same, okay? If you try to make some expansion on a smooth object, you see that you have some relationship between your two kernels that appear in the Taylor expansion that connect them in this way, okay? So Now, what about the convergence of this approximate curvature? Well, first, consistency. If I take a smooth object and I compute h epsilon, my approximate curvature, and I compare it to the true one. Well, this is, let's say, the nice case, and this works quite generally, even if you have an object that is only rectifiable, and as soon as you can define a generalized curvature on your object, then you will have convergence of the approximate one. So for the consistency, it's not difficult. What about the convergence, okay? The stability question. The question is, if I take a smooth varifold, or regular enough, okay, and a sequence of varifolds, think of point clouds, but it could be any varifolds, that get closer and closer to my continuous object, okay, for instance in flat distance, can I say that my approximate curvatures, both of the continuous object and the discrete one that approximates my continuous one, can I say that those curvatures get close? Okay, it's more like a stability question, and usually it's more difficult. And okay, the answer is yes, and that's why maybe varifolds are a nice framework for curvature, because it's usually not easy to have a positive answer to convergence, pointwise convergence question of curvature. Okay, so you have a positive answer, and here this is your regularization parameter of approximate curvature. Here is the point of your discrete object where you are computing your approximate curvature, and here it's the point in the limit object, the continuous object, where you are looking at the curvature. Okay, so you want that those points are close enough, okay, and smaller than the regularization parameter in order to have your convergence. And here you have a term that encodes the fact that in flat distance your discrete object and limit object are close, but it's not directly the flat distance, it's a kind of localized flat distance. You have to redivide by the local mass, okay. So it's a bit technical to write, that's why I didn't write it. And under this assumption, you have some stability property, okay? And here is hidden the flat distance term. Okay, if now I rewrite my expression for a point cloud, that's the expression I get, okay? So I'm going to show you numerical illustrations of this approach on point cloud, okay? You could try another structure. It's on point cloud, it really makes sense because you don't have much structure when you have a point clouds. Okay, you have basically points. So when you put a varifold structure on them, well, you won't lose anything. Okay, if you take other objects, you have to think of the balance between. Okay, you have this nice formula, but maybe you are losing some information on the connectivity of your object, maybe on the orientation. If you were using it, then you will lose it with varifold approach. Okay, but for computing curvature, you don't need all that stuff, okay? Curvature is not, actually, mean curvature is not about topology, is not about, I know, it's not about orientation, okay? Vector curvature. So it's normal that it's not necessary to use them to compute it. Okay, so now, sorry, you take this formula, you take a point, for instance, in your cloud, and well, if you want to compute this thing, you just have to go to every point. Okay, okay, you take a point. Sorry, you look for the neighbors. Okay, so with maybe a KD tree algorithm, something like that. Okay, at each point you need to compute a tangent direction. Okay, by standard weighted least square regression, for instance. And the local mass, okay, that is maybe a deeper question because it's not clear how to compute masses in order to have something that is an estimator that is convergent. Okay, you have ways to compute local densities. Okay, but then the convergence on those techniques is not clear. So once you have that, you just apply your formula to your neighbors. Okay, here it's not a sum over all the cloud, because here you can take a kernel that is compactly supported with a small support of order epsilon. Okay, so it's not a huge sum here. It's just a sum in the neighborhood of your point. So it's reasonable.
In practice, what is the size of your neighborhood?
Well, it depends, but let's say that we don't have a good way to choose it. Okay, we have the same problem than any person working, for instance, with a point cloud. The theoretical answer is that you must be larger than your flat distance between the discrete object and the continuous one. That you don't know, of course. So you must be larger than some kind of measuring the quality of your discretization. Concretely, let's say 40, I don't know, 40 points, something like that, on the surface. Okay, but it depends on. It really depends on your. We don't. Okay, we did not tackle this question that is a huge question to define good neighborhoods in point cloud, for instance. Okay. So let's take a point cloud. Okay, so here it's something like 400,000 points. Okay, if you want to know. And here, if you have a diameter 1, here it's not a number of points that had been taken, but a size of ball. Okay, but it must be around 50 points per ball, something like that. Okay, and first compute the mean curvature vector. Okay, so here you have the intensity of the mean curvature vector. Okay, so from very low mean curvature, blue, through very high mean curvature, red. Okay, so I told you there is no need of an orientation to define the curvature vector. If you want to recover the algebraic curvature, of course you need an orientation, because the algebraic curvature is defined with respect to the normal orientation. Okay, so here you don't have this information. Okay, and I don't have time to explain how, but you can really apply the same kind of techniques to get more than the mean curvature, but actually the second fundamental form. Okay, based on biparts integration on varifolds. Okay, you can also recover the second fundamental form, and as for the mean curvature, you will then recover, for instance, your principal curvature up to a sign, but not each one, but up to a sign. Okay, you have a relative. You have their relative sign. Okay, not their absolute sign if you don't have orientation. If you have an orientation, then you can recover it afterwards. Okay, so you have the Gaussian curvature because you have the relative sign of the principal curvature. Okay, so this is what you obtain if you apply the same kind of techniques. I can show you the ugly formula afterwards if you ask me, but I won't if you don't. Well, it's not more it's ugly, but it's not more difficult. It's the same approach. You make some computation with the regularization kernel in the neighborhoods of your point. Okay, with mass and tangent information, nothing more. Okay, so you can compute Gaussian curvature. You can compute the absolute sum of the principal curvature. Okay, to try to detect sharp features. You can do that also on objects that are not regular, okay, as this cube. You can add some noise. You can see that the computation of the Gaussian curvature when you add some noise is not very nice on the edges. But for the sum of the two principal curvature, it's okay for me. Okay, and last but not least, then once you have your mean curvature, you can try to flow it, okay, to make some mean curvature flow. And the idea is that your mean curvature that is defined on a point cloud. So why not trying to flow it, to flow each point with the mean curvature you compute? If you do it with an explicit Euler scheme in time, well, as usually, this will blow up unless you take very, very small time step. But if you try to define an implicit scheme, so this is a joint work with Martin Rumpf. Well, the first part was a joint work with Simon Masnou and Gian Paolo Leonardi. I should have said that at the beginning. It was written, but I didn't tell it. So if you do it in an implicit way, okay, you can manage to obtain nice, for me, nice flows in singular situation. Okay, so start with a square and fix the corners. Okay, and you might know that if you have 4 points in the plane that are just the corners of a square, then if you look for the least length, the shortest path that connect the 4 points, then you can obtain 2 different Steiner tree. Okay, so with 2 triple junction that connects your 4 points. And as the mean curvature flow is known to be the flow that minimizes the length, the natural question is, well, can we recover that at least? Okay, so if you start from the square and fix the 4 corners, then and tune your parameters. I'm not saying it's working for any parameters, unfortunately, but you can obtain a nice evolution of your square to one of the Steiner tree, okay? And depending on the parameter you choose, you can obtain one or the other, okay? So maybe I'm just going to show you one of them because the other one is quite similar. Okay, here there is some kind of, it's not completely regular in time, or it's just because instead of recomputing the cadet tree structure at each iteration, it's computed every maybe 10 iteration. Okay, it's some technical stuff. And it's going to stabilize close to the Steiner tree structure. Okay, and then stay this way. Okay. And maybe last. No? Yes. Okay. You can do the same thing with a cube. Okay. So you take a cube and only the lateral area of a cube. Okay. So the 6 faces, and you discretize them in point cloud, and you fix the edges. Okay. So you fix the edges, and you ask yourself if when computing your discrete flow, you will converge to something that looks like the Brachy cube, okay? So that is expected to be a minimizer of the plateau problem so that minimizes its area when attached to the edges, okay? And so here you have different steps of the flow, okay? And you see that there you have a small cube that shrinks in the middle, and at some point actually the cube is just 1 point, and you have a cone on the edges, and then this cone is not minimal, okay? It's not a minimal cone. You can do better than the cone on the edges in order to minimize the area, okay? The idea is that you can just push around your central point, okay, in this way, or this way, and flatten the central area and create a small square. And this is, the exact profile of the surface is not known, okay, but the global aspect is this one, and so we are not far from it. So in one direction, when looking in one direction, you have this square, and from 2 other directions, okay, you just see an edges. Okay, it's really a flat square in the middle, and it's consistent with what is expected. Okay, I think that the square might be a little wider, so it's not perfect, but quite nice to me. Okay, and okay, no, that was the ugly formula. Thanks for your attention.
Thank you very much. Are there some questions or comments?
So instead of the flat norm, is it possible to consider Euclidean norms like a kernel distance or things like this that are used in statistics a lot?
Good question. I don't have exactly the answer, but I would say maybe, because the idea is that you need to control the integral of some kernel on your object. Okay, you don't need to have all the continuous function on R and times the Grassmanian. So that might be possible, yes. That
Lipschitz is not really very important.
Yes, Lipschitz is important, but if you take a kernel that is Lipschitz, I mean, one Lipschitz is not important. So I would expect it could be possible, yes.
No, that. I was wondering, it's very nice work, if you have managed to reach out to the computer graphics community with these ideas.
Well, not that much, but I must say that it's kind of also because we did not benchmark it. So, and I understand that then people probably don't want to get into all this technical stuff if they don't know that it's, okay, really more efficient from a computational aspect than what exists. So I would say that's also because that. Well, not the computer graphics. Some people working more like on digital surfaces were interested. So yes, that's and people in mechanics, much more like. So well, that's it.
Okay. Okay, if there are no further questions, I think it's time for the coffee break. Thank you again.